let us finish up this part 1 and go on to part 2 of chapter 12. We want to hopefully get through chapter 12 today. So how is everybody so far on chapter 12? It's a little... Are we on chapter 12? Yeah. It's a little mind-boggling, but like I say, follow your outline. What did you say? No, we can't go back to chapter 1. This is almost 1. There's a 1 in the number, right? And a 2. So I'm not kidding about the difficulty, but remember, you want to wear a path in those little brains to the file cabinets where your information is stored so that you will remember this information and access it easily, right? And how will we do that? Repetition, repetition, repetition. Use, again, look at it a different way. So don't just read your book because, right? So go and use the other tools. Go and use that interactive physiology. Go and use some of the other resources you have in that mastering file for chapter 12. Okay? Maybe even listen to the lecture over again if you don't do that on a regular basis. Okay? So don't just rely on reading the book to get it, because this is a tough one. All right, so we're on the brain stem. 3 major regions: midbrain, pons, and medulla oblongata. What we're going to see here in that brain stem region is some of the lower, what we call lower brain function. And also remember, we're going to find a lot of white matter tracks that are leading from the spinal cord to the rest of the cerebrum and all of those other regions we've already discussed. So not only are we going to find nuclei for processing here, but we're going to find a lot of white matter tracks to other places. Does that make sense to everybody at this point? If it doesn't, you've got a lot of work to do. Okay? So, we're going to find some similar structures in the brainstem as we do when we discuss the spinal cord. Again, a lot of pathways up. Controls a lot of autonomic behaviors. And this was the nuclei I was just mentioning. Groups of cells, files for information for autonomic function. When I say autonomic function, what does that mean? Automatic, visceral stuff, things like heartbeat, things like breathing, things you can't have conscious control over. They are controlled by something else. Well, this is the something else that we're talking about. We're going to connect some lower neural centers, autonomic centers here in this region of the brainstem, and then nuclei associated with 10 out of the 12 pairs of cranial nerves. Well, what are the cranial nerves? First, review. What's a nerve? A bunch of neurons. And what are the cranial nerves? Yeah, one's in your head. Now, stimuli from here. Sensory neurons. Are they going to send information to the spinal cord and then up to the brain? That wouldn't make sense, would it? So many of those cranial nerves, there's a couple of exceptions, will send information from this region for processing in the brain. So when I get stimuli from light hitting the eyes, where does that information go? For processing in the brain. What part of the brain? The occipital lobe, which is back here, yes? Cranial nerve number 2, your optic nerve, is going to send information from here to there, yes? Cranial nerve number 1, your olfactory, is going to send information from here to there, yes? There's 12 pairs of cranial nerves. You're going to need to know them all. You need to know them by name. You need to know them by number. And you need to know a basic function for each. That's coming. Don't panic. But just a heads up. So, we have connections there for some of those cranial nerves down in the brainstem region. When we dissect our sheep brains, pay close attention to this. You can see them all kind of lined up nice for you here. Here we have cranial nerve 2. How many eyes do you have? 2. Cranial nerve 2 is for sight, yes? How many noses do you have? 1. Cranial nerve 1 is for smell. See, I just taught you 2. Yes? So here they are. And you can see them all feeding in on the sides here in that brainstem region. So we'll learn them. In this diagram, we can see them a little bit better. But the thalamus, the hypothalamus, the midbrain, the pons, and the medulla oblongata are in this diagram. The purple region that we talked about at the end of class, last class, the diencephalon is here. And then the brainstem that we're going to talk about now. Those diagrams are in your book on page 444, figure 12.13.
So the olfactory is not on that diagram?
No. Yes. No, it's not. I'm sorry. I think only 2 is. Olfactory is a little bit higher.
Okay.
Let me see if it's on the brain. No, now you get me sidetracked. Yeah, it's on the brain. Here it is. Olfactory bulbs up here. And ours are dinky. When you do your sheep brain, you're going to see they're much, much bigger because other animals have a much better sense of smell and use it for a lot more things than we do as humans. So these are some areas that we find in midbrain regions, some connections, some white matter connections, the cerebral peduncles. And then we also find a connection for that cerebrospinal fluid to flow in the cerebral aqueduct. We're going to connect the 3rd to the 4th ventricles. Everybody knows what a brain ventricle is, right? What is it? It's a space that's filled with cerebrospinal fluid. How many do you have? 4. That was my Boston accent coming out. I'm sorry. So, in those midbrain regions, we're also going to have groups of nuclei that are going to do some processing for us as well. So we have links to the amygdaloid bodies for the autonomic nervous system functions, automatic control. We also have some groups of nuclei that are going to process things for visual reflexes, for auditory relay centers. Again, remember those cranial nerves that have to process information for all of those things that are happening up in your head. Sight, taste, smell, sound. We're going to talk about these in more detail next semester when we hit chapter 15. That basal nuclei that we talked about earlier, we find some links to that as well. And then we find some links to the reticular formation that we talked about earlier as well in this region. This is a little map of some of those things we just mentioned. What's the cerebral aqueduct? Correct. So that's that little hole that runs all the way down the spinal cord that allows for flow of cerebrospinal fluid. And then all of the things we just mentioned above are mapped out here for you. In the pons, we see that 4th ventricle separates the pons and that back little guy that we're going to talk about in a minute called the cerebellum. Again, we're going to find fibers and connections to higher brain regions from the spinal cord here. In the pons, we're going to find the origins of some of the other cranial nerves like 5 and 6 and 7. The trigeminal, the abducens, and the facial. Again, each of those controls certain function in the cranial region. Nuclei also found in the pons are going to help with the breathing and the rhythm of breathing. They're called the pneumotaxic and apneustic regions. Don't worry about that. We're going to talk about it when we talk about the respiratory system. But remember this discussion, because when those come up again, you know that they're going to be in the pons. Again, another map of that region. I'm not going to make you memorize the map. Right now, we're laying a foundation. We want a base knowledge to understand how the brain is related to all of those other systems when we discuss them. Because when we discuss all of those other systems, we're going to talk about the brain's contribution to their function. Okay? So now we're laying the base knowledge. The medulla oblongata joins the spinal cord at an area, big hole in your head called the foramen magnum, at the base of your skull. Do you have to know where that is? Yes, you do. So remember where it is on your bones, and that's where we're going to find your medulla oblongata. So it forms part of the ventral wall of the fourth ventricle, contains groups of cells that make cerebrospinal fluid called choroid plexuses. And then we're going to find, again, connections to higher brain regions. These are all connections. So basically, we're going to find these different connections that relay sensory information from muscles and joints to the cerebellum, who we're going to talk about in a minute. Now, what's the cerebellum's function in all of this stuff? Muscles and joints. Take a guess. It's going to help with what? Motor. And coordinated movements of those guys. Yep. So we need to coordinate those movements. Remember my discussion last class kind of boggled a few of your minds when I talked about all that was involved in me just walking across the stage. So all of that coordination has to be sent through relay stations in higher brain regions. The medulla oblongata is going to help channel that information through the cerebellum. We also have connections to cranial nerve 8, 9, 10, 12. We have nuclei that are going to help us maintain equilibrium connected to some of these cranial nerves. When we talk about the inner ear next semester, we're going to talk about cranial nerve 8, the vestibulocochlear cranial nerve 8, which has two branches, the vestibular branch and the cochlear branch. Don't panic. We'll talk about it next semester. But the vestibular branch is going to send information from little canals full of fluid called semicircular canals. And every time I do this, guess what happens to that fluid? It moves, and it's going to fire off neurons that are going to help send information with respect to where I am in space, equilibrium. I also have a branch of vestibular cochlear cranial nerve 8 that's going to send information from the cochlear region of my inner ear, and guess what's in there? Receptors for hearing. And they're all located in the same place. Okay? We also have several different nuclei that are going to relay other sensory information. Cardiovascular centers are here as well. That's going to adjust your heart rate, adjust blood flow. When I hear that there's hermits up in the bookstore, I'm immediately going to run up to the bookstore to make sure I get my fair share. Yes? So what has to happen? As I'm running to the bookstore, somebody's going to tell my heart to speed up a bit because my muscles are doing what? Contracting faster, using up more oxygen, so they can make more ATP. Yes? So in order to satisfy the need, I have to speed up my heart rate and I have to speed up my breathing rate so I can make it to the bookstore on time for my delicious hermits. By the way, don't miss the hermits when they come to the bookstore. They're quite tasty. So, cardiovascular centers in the medulla oblongata are going to help regulate rate of cardiovascular function. Vasomotor centers. What's a vasomotor center? What's a vaso? Yeah, vascular, blood vessels. And those have to be regulated as far as whether they're skinny or whether they're wide, whether they're constricted or whether they're dilated. If I dilate a blood vessel versus constrict a blood vessel, I'm going to change flow to an area. Okay? So that's where we're going to find them. We also find functions that overlap in the hypothalamus or with the hypothalamus to relay autonomic reflexes. Respiratory centers. I'm going to need some extra oxygen as well as blood to deliver it when I'm running up to get my hermits. So we find those there in the oblongata as well. We also have additional sort of reflexy centers, vomiting, hiccuping, swallowing, coughing, and sneezing in the medulla oblongata as well. We'll talk about these guys when we talk about the respiratory center and the digestive function later on next semester. So again, a map for you of where we're going to find all of these places in the medulla oblongata. Clicker time! You got it, girl. The pons belongs to which major brain region? Only 33 today? There's more than 33 bodies out there. 5, 4, 3, 2. Poke a number, poke a letter, do something, just so I can know you're here. You done? Brainstem is the answer. D. We haven't talked about the cerebellum yet. The brain contains how many ventricles? All right, 5, 4, 3, 2, 1. What's the answer? 7. Oh, E? There is no E.
Well, does she know they're here?
Oy vey. The blank of the brain is the location of our this is the location of our conscious mind. And yeah, there's the answer. My conscious mind is asleep right now. Everybody click the right answer so I can say, woo, everybody got it right. E, mother of pearl. All right. Why is this doing this? Oh, E again. 2 people, 2 jokers. Yeah, I was going to say, you 2 probably. No. Oh, sugar. All right, the cerebellum. E. I know we haven't talked about the cerebellum yet, but we're going to talk about them now. Five, 4. Yeah, it is. It is a slide. It's not a question. It's all of the above. I know. I'm like, why isn't there an all of the above choice? I'll pick E. There you go. Oh, it's okay. I'm tired. I'm looking forward to the end of this week. Okay, so the cerebellum is 11% of the brain mass, dorsal to the pons and the medulla. It's all of the above, and it's going to help allow for smooth, coordinated movements. There's 2 hemispheres to the cerebellum in humans, very distinct, and they're separated by a little connection called the vermis. When you look at diagrams of it, kind of looks like a little worm, and that's what vermis is, that runs down the center. Then we have transversely oriented gyri, which means they go off to the side bumps. And each hemisphere has 3 lobes, anterior, posterior, and one called the flocculonodular. When we open up the cerebellum, we're going to see lots and lots of white matter tracts connecting all of those tendons and muscles for coordinated movement. And it looks like a tree almost. So when you dissect your sheep brain, pay close attention to that. Those white matter tracts are called the arbor vitae. And that actually means the tree of life. Yep. So we can see them quite clearly when we dissect. And we see all of the gray matter here as well. So we see that there's many groups of nuclei that are going to help to coordinate all those movements. And we see that white matter running right through the center and off to the sides in branches. That's one of our little diagram pictures so we can see it better. And then, of course, our cute little diagram of what this portion of the brain controls. So, all fibers in the cerebellum are ipsilateral. And that means what? Yeah, left controls left, right controls right. Okay, a little bit different than how the hemispheres were set up. Okay? So located on or affecting the same side of the body. 3 pairs of fiber tracts connecting the cerebellum to the brain stem we find here as well. Connections to midbrain, connections to pons, and connections to medulla. All of these are called pedicles. So we're going to get impulses, muscle. Impulses from proprioceptors to help coordinate those muscle movements. What were proprioceptors again? Spatial stuff, right? To help coordinate movements. Now, not only does those semicircular canals in my inner ear help coordinate movements, but visual does too. Do you ever feel like you were off balance sometimes when you were going to walk somewhere weird? Yes, and alcohol does affect your proprioceptor abilities. So, I have a problem. Anybody ever walk up a fire escape? You know those stairs that have all the holes in them as you walk up? I have a problem with those. I feel like I'm off balance when I go to walk up them. I can walk upstairs just fine. Why does that mess me up? Because visual receptors are also giving me information as well. So it's not just the proprioception doesn't only come from those equilibrium receptors, but they're also contributed to by visual pathways as well. Coordination, movement. And pretty much that's going to be repetitive in all of these slides that we see to come. So, role in thinking, language, and emotion is also part of the cerebellum's coordination. That's the end of this part 1. Let's go to part 2. So, two formations, limbic system, reticular formation. Aren't things I can go and grab as parts, but these are nuclei that are scattered throughout midbrain, lower brain, and upper brain regions that are going to help coordinate function. In the limbic system, we see nuclei dotted throughout the diencephalon, and some in the cerebrum. Many of them circle the brainstem. This is a diagram of where those nuclei can be found. And what's the limbic system for? Well, we have a bunch of different things that are going to help connect information to files in upper brain regions that affect emotions, fear, anger, when danger is abound. These guys are going to help coordinate movements. When you are afraid, what are some of the things that might happen to you?
Start sweating. Heart rate goes up.
Yeah, you feel those effects. You might sweat, you might shake. You might get angry too when you're afraid. So a lot of these are located in the limbic system. So emotional responses can be associated with the limbic system. Some of these pathways are very, very closely connected to odors. Okay? So emotions can also be connected to sometimes to things you smell. Not only bad emotions, but good emotions and good memories. So since the holidays are coming up and Thanksgiving is right around the corner, think about what happens sometimes when you're all maybe around cooking Thanksgiving dinner and somebody's cooking, say, your favorite. I enjoy the pumpkin pie myself, and you smell that in the air. Can that elicit some memories or feelings or emotions? Okay, so they're quite close in their pathways. That's why this happens. So most of the output is relayed via the hypothalamus, that good old hypothalamus, busy, busy, busy. So, reacts emotionally to things we consciously understand to be happening, processed in the limbic system. The hippocampus is also going to play, which is an area of the limbic system, is going to play a role in memories. And that's where the good smells of Thanksgiving come into play. This is sort of a pathway that we follow in those messages being transmitted through the limbic system. Hypothalamus, thalamus to cerebral cortex, cerebellum and spinal cord are also involved. The reticular activating system. Again, a group of nuclei that's going to help coordinate information that's being sent through those massive white matter tracts in those central brain regions. This is the area that filters out a lot of stimuli that if you were aware of all the time would drive you crazy, literally. Think of all the stimuli you're experiencing right now that you don't even really pay close attention to. I'll give you an example. Any girls have ponytails? See them? See them? You are now receiving stimuli through your central nervous system from every hair follicle in your head that's being pulled on by your ponytail. Can you imagine being aware of all of that? You're all sitting on your keisters, firing off pressure receptors in your butt. Are you aware of that? No. Light is being sent. You're looking at this, but you're getting light from lots of different directions. There's actually things in your visual field, all the people around you, all the chairs around you. Are you aware of those things? You are now, because I just pointed it out. But can you imagine if you didn't have your reticular activating system to filter out all of that excess information? You're receiving it. It's being processed, but you have the ability to filter it out. In some people, that is lacking. So that can be totally overwhelming to some people. Exactly. And some children that are experiencing some of those disorders don't even want to be touched because that's extra stimulus for them that they are aware of at all times. So, injuries to this area, reticular activating system, can result in coma. A lot of motor function relates to the reticular activating system as well. Some of the larger movements of your limbs. Some of the regulation of vasomotor, again related to cardiovascular system with the cardiac center, and respiratory centers are relayed through the reticular activating system. So this is kind of a crazy diagram, but this is where those messages are being sent from different groups of nuclei in the reticular formation throughout the cerebral cortex. We can measure patterns of electrical message that are being sent through the brain. By the way, before I get too far ahead of myself, on page 450 and 451, you see one of those handy-dandy tables. That might help as well when you study. So you can see table 12.1 that goes on to both pages that gives you a nice overview of what all of these different parts do for a living. EEG measures brain waves. What's an EEG? Electroencephalogram. And that's going to record the actual electrical events that are going on in your brain. Remember, every time we have a nerve impulse, a neuron firing off, an action potential, that has a measurable wave of electricity. And that's actually what is being recorded in an EEG. So we can measure some of the different electrical potentials going on in various areas to find out whether we have normal electrical events occurring or if we have abnormal electrical events occurring. So, some of the different patterns of electrical events can be measured in an EEG, and they're measured in 4 classes. We have alpha, beta, theta, and delta. And we measure them in something called hertz. So, the different types of brain waves that you experience on a regular basis, alpha, 8 to 13 hertz, is a nice regular rhythm. Oops, wait a minute. And we see alpha there. We can see this on page 453. Oops, where am I going? In your textbook. So, regular rhythmic, this is when we say your brain is kind of in idle. Now, what's idle make you think of? Yeah, it's kind of chill. It's kind of, I'm waiting at the stoplight, ready to race the guy beside me, chill, right? With respect to what's going on electrically in my brain. Alpha, by the way, is the best wavelength to be in when you want to learn something. When you are stressed out and in different brain wave patterns, you're going to have trouble retaining memories. So what's the best way to be when you study? Chill. Sometimes you fall asleep because you're so chill, but make sure you're not too comfortable when you get into your alpha waves and you study. Beta waves, 14 to 30 hertz. And again, these are more, and if you look at page 453 in your textbook, we see them more frequently. They're less regular and occur when you're very mentally alert, or maybe when you might be a little less chill. Theta waves, much more irregular, 4 to 7, much more lower, common in children, but uncommon in awake adults. There's a lot of brain building going on, but when you're all built up in your adult stage and we start to see a lot of theta going on in your brainwave pattern, there might be a problem with your electrical system. And then delta, high amplitude waves, deep sleep. That's when your reticular activating system is kind of resting and rebuilding for the day to come. Yeah, those are the brain waves you see when you go through the different stages of sleep, and we'll talk about those as well. If I see them in awake adults, that can be a problem. So that can indicate some problem with proper electrical function in the brain. And we see that other part of the diagram. So, as far as brain waves go, they can be measured to help determine whether brain function is normal. They're going to change with age. They're going to change with different stimuli. Different diseases might cause problems with your brain wave patterns. Different chemicals might cause problems with your brain wave patterns. And not just chemicals that might be prescription. Other chemicals as well, which you might encounter in your lifetime. They are going to alter your brain function. And that's pretty much all the chemicals that you might come in contact with. Not only drinkable, but smokable. Yes? When you alter brainwave patterns, this is sort of a misconception in the younger world these days. They seem to think that that's not really a problem. Some of the chemicals you might come in contact with. But anytime you alter your brain function, you might potentially be damaging your neurons. When you kill and damage your neurons, you don't get them back. So my advice to you is don't take the advice of those who take their chemicals lightly, because I want all of the neurons that I can hold on to for as long as I possibly can hold on to them. Yes? That's for a reason. So, EEGs are also used to diagnose some of these different disruptions. So any lesions or localized brain problems, any tumors. What's an infarct? Like a blockage. Yeah, like a stroke. Anything that prevents blood flow to an area is going to result in areas of the brain that might start to die off. Any infections, abscesses, you can read just as good as I do. Flat EEGs, not good. Yes? That means no electricity is flowing through the brain. And this is usually how someone diagnoses whether or not you are brain dead. You might still be able to have lower function induced, but the file cabinets are closed for good. Epilepsy, what is it? Well, it's when your electrical system goes a little wacko. So when things start to fire off in patterns that they shouldn't normally be firing off in, that's usually what we define as epilepsy. Now, yes?
When you have epilepsy, you're misfiring, right? Like your mild sheets.
You might be excess firing or not firing enough. Usually it's an excess firing.
Trying to associate it with multiple sclerosis.
Different.
Yeah, do they have seizures?
Not typically. Multiple sclerosis usually is a demyelinating event. So instead of firing off too much, what are you doing with a demyelinating disease? Or not firing enough because it's too slow. Okay? May see the difference? So, epilepsy is not associated with intellectual impairment. So that's a misnomer. 1% of the population has an occurrence of epilepsy. And you might start to fire off neurons, sensory neurons, that will actually allow you to perceive your seizure coming. You might feel a change in visual stimulus, or you might hear a change in auditory stimulus. Some people that are ready to experience a seizure might even start to taste something funny or smell. Exactly. Yes?
Now, are those the same neurons or whatever that would be sending out, like if you get aura with like migraines?
Yeah, yes. Those are affecting some of your visual sensory problems as well. So sometimes people, huh?
That'd be like when people go to have their picture taken, flash sometimes, depending on the person, cause epileptic seizures.
Yeah, or like strobe lights or different visual stimulus can set off seizure events as well.
Or like dunking underwater can do it.
Yeah. Oh, there's so many different stimuli that can set off this sort of stimuli firestorm that results in seizure. Sometimes when people are ready to have a migraine, they see tiny little sparkles in their visual field. And sometimes their visual field starts to look like a tunnel almost. Has anybody ever experienced that? But those are some of the visual stimuli or auras that you experience before a migraine. And a migraine, can be caused for many different reasons. Constriction of blood vessels, but can also cause problems with abnormal firing off of electrical events in the brain. So there's different types of seizures. Petite mal seizures, we consider mild seizures, young children. So there's not a lot of muscle contraction there, but as far as response to other stimulus in the environment, that slows a great deal. Then we have the more severe seizure, which most people associate with seizures, where we have lots and lots of muscle contraction going on. They might lose consciousness because of the violent movements. They might even break bones, but you have a lot of intense muscular involvement in a grand mal seizure.
In those types of seizures, will they also like tear muscle?
They could, yeah. So all of those things listed under there could occur during this type of seizure. Different drugs, anticonvulsive drugs might be prescribed to somebody having epilepsy or in any of these forms of diagnosed epilepsy. The vagus nerve, sometimes that's cranial nerve 10, might be involved in some of the messages being sent to all of that muscular involvement in seizures. So helping to slow some of those impulses might help patients with epilepsy. Consciousness. Most of you, hopefully all of you, are conscious as we speak. With the help of your reticular activating system and your limbic system, you have conscious awareness of what's going on around you. Loss of consciousness signals that the brain function is slightly impaired. Anybody ever faint when they might be getting sick?
Not faint, but when I see blood.
Okay, that can happen too. So loss of consciousness signals that brain function is impaired for whatever reason. And again, sometimes this happens to people who are starting to get a fever, starting to get ill, or see something, in your case, disturbing, that can cause them to lose consciousness quickly or temporarily. Consciousness, clinically defined as a continuum that grades behavior in responses to our stimulus. So, awareness of your environment, alertness, drowsiness, involves simultaneous activity of large cortical areas. Again, that reticular activating system and limbic system are firing off and calling on a lot of the files that you have in your upper brain regions and cerebral cortex to deal with what you're going on in the conscious world. Narcolepsy, the sleeping disorder? What's going on? I don't know. Good question. Yeah, there's...
I don't get into delta sleep, but...
There's all different reasons why people do that, and there's different,
Some people just like, they have to wear a helmet or whatever because if they'll like walk. One day I was at the grocery store and I walked down the aisle.
yeah, that's, well, my point was there's definitely different intensities of the disorder, narcolepsy. Reticular activating system and limbic system.
in the center of the stem, that's what it feels like.
Yeah, and again, it's those pathways that are connecting all of that conscious stimuli for a response from you. Again, many different reasons why that might be affected. Could be chemical reasons, could be pathway reasons. Sleep. Why do we need to sleep? When we think of the nervous system and sleep, we should think of repair. Repair needs to be done during sleep. So sleep is extremely important. Now, are you conscious during sleep? No, you are considered what? Partially unconscious. Can you respond to your environment if you have to? With extremes, yeah, you do. Most of us do that every morning. Respond to our environment while we are partially unconscious. I did it this morning. Yeah, when your alarm clock goes off. Yeah, or when you're getting whacked by the dog, when she lays all of her 65 pounds on you and decides it's time to go on. So, you are partially unconscious. Two major types of sleep defined by our EEG patterns, those electrical brain waves that are measurable, are non-rapid eye movement, NREM, or rapid eye movement, REM sleep. If you look on page 454 in your textbook, figure 12.19, we see what some of these different stages look like on the EEG. So, sleep. First you pass through the first two stages of non-rapid eye movement. Then we pass into stages 3 and 4, where our brain waves start to slow down during the first 30 to 45 minutes of sleep. At about 90 minutes into our slumber, after the fourth stage, we begin something called REM sleep, rapid eye movement. And it's kind of freaky if you watch people sleep. Do you ever watch somebody sleep? Maybe because you was bored or something, or you were a stalker, I don't know. But all of a sudden their eyes will start to do what? They'll start moving.
But in the narcolepsy, you do the REM right away.
Yeah, because you don't flow through those stages of sleep in the proper order.
Feel like
The book
you're-
actually has a homeostatic balance on narcolepsy.
Yeah, on page 455. So yeah, some of the different categories would be things like insomnia, sleep apnea, All right, so at 90 minutes after fourth stage, REM sleep begins. Rapid eye movement and EEG, heart rate, respiratory rate, blood pressure, GI motility, all will change. You might even be in what we call temporary paralysis. Way more difficult for you to respond to that dog on your chest or that kid whacking you in the head telling you to wake up. It's hard for you to do it when you're in that stage. So these are the different stages and what brain waves look like, hopefully. When you are awake versus REM, things start to do what? They're not as rapid. They start to slow down brainwave wise. And then all of the stages are defined here. You should have a general understanding of all of the different stages of sleep. So as you sleep in any given evening, you are going to cycle through these stages in a nice rhythmic way. This is called your natural circadian rhythm. If you don't do that for whatever reason, you aren't going to feel very rested when you wake up in the morning. Even though you might have slept, you wake up and you're tired. Sometimes when people can't fall asleep, they take medications to help them do that. Yeah, and so you go to the drugstore and you buy yourself a sleep aid. The problem with those is they also don't allow you to go through your natural circadian rhythms as well. So you're kind of stuck in the beginning with a sleep aid. So you might fall asleep, but again, you wake up the next morning and you still feel really tired. And it has to do with the fact that you're not able to flow through those different rhythms. They do studies called sleep studies that involved EEGs. And they can actually go in and look at what the problem is electrically with your sleep and maybe help you by doing a sleep study.
They actually have the medicine, but it's so controlled. It's like the date-breaking drug type stuff.
Mm-hmm.
And it throws you into the delta and theta waves. But you have to take it after 4 hours again. But it's so controlled.
Yeah.
It's unbelievable.
Yeah. And again, anything, we think about the brain now, hopefully a little bit more seriously, but some of those drugs that control these brain waves are they can be very tough.
I mean, you have to be there to receive it every month. Nobody else can receive it.
Yeah.
Government center.
Exactly. So typical sweep. I need a little sweep myself. Typical sleep patterns alternate between the REM and non-REM sleep. So in any given night, hopefully if you're getting a good night's sleep, you are going to alter or go through rhythmically, these different stages until we wake up in the morning. So as we get to the end of our sleep, we notice we don't fall down into stage 3 and 4. We start just cycling through those beginning stages when it's time for us to awaken.
In the book, it says the fourth stage, non-rapid eye movement. Does bedwetting, night terrors, and sleepwalking may occur?
And this is when you're in a deep, deep sleep. So and usually it happens younger. Not always. It can happen older as well. But this is when I'm in such a deep sleep, I have trouble responding to the environment outside. So if we're getting stimulus that our bladder is full, some people can't respond to that and might wet the bed. Some people might be dreaming so vividly that they might also have problems, and that's the stage, because they're in such a deep, deep sleep.
And with kids, their pelvises they're still soft, and they can relax on the bladder and that.
Exactly. And then the myelination of those different neurons too is quite young as well. So it's hard to control those functions. And just the fact that you can't respond to the stimuli is a factor. So we need sleep. Slow wave sleep is very restorative sleep. So in those stage 3 and 4, that really deep sleep, that's when I'm doing the road work. That's when I'm rebuilding. That's when I'm packaging up all of those chemicals in my photoreceptors. That's when I may be repairing some of my myelin sheath that might have been degenerated during the day. That's when repair work happens. So people deprived of this sleep can become very moody, maybe even depressed. When I'm very tired, everything is funny. Have you ever gotten into that stage? Everything is funny. REM sleep may be, why can't I read today? Thank you. Reverse learning process, where information is being purged from your brain. Daily sleep requirements decline with age, but also you don't sleep as much when you get older, because you don't need to sleep as much when you get older. See, there's a reason for all of this stuff. It just is not fair, because when I had my children, I enjoyed my sleep, but I didn't get any. And now that my children are older and they enjoy their sleep, I can't sleep that much anymore. Huh? Try to wake them up. I have an air horn in my house. My children hate me. Step 4, sleep declines steadily and may even disappear after the age of 60. Narcolepsy, under homeostatic imbalances, again, for different reasons and at different intensities, is going to lapse you into sleep and awake states. Orexins are wake-up chemicals from the hypothalamus that are destroyed by different immune system responses. So you might have trouble awakening. Insomnia, problems getting into these normal rhythms of sleep, may be treated with some of these orexin blocking actions. And then sleep apnea, absence of problems with falling asleep, may have the result of messing with your respiratory system as well. Yeah. And when my husband starts snoring, I sit there and listen, because he'll snore and then all of a sudden it'll stop. And then he'll do it again. That just freaks me right out.
My husband
So.
would stop for a minute and a half at a time, and when they did the sleep study, they said, the first thing they said to him when he woke was, your wife must be crazy. Started breathing 158 times.
Wow. Yeah, so it can be quite dangerous. So has anybody ever seen one of those CPAPs? It forces you to have that normal breathing rhythm. Cannot be very comfortable. Does anybody have to wear one in the room? Yeah. Yeah, and it helps with those, it helps keep you in normal breathing rhythm. Can cause hypoxia, not absence of, but very severe decrease in what? Oxygen levels. Basal nuclei, Broca's area, helping me with language, getting information, sending information, coordinating information to help produce words. So they talk about language on page 455 and 456. Now, right side of the brain, corresponding areas on the right side of the brain involved in nonverbal language components. So not only speaking and making sound is part of your language. What else do you have to do when you speak? And I do this quite a bit. I talk with my hands. There's eye movements, there's facial movements that are associated with that. There's motor movements involved with the mouth to form some of the different words that you create in your speech. So all of those things have to be coordinated for speech to occur. The next thing they talk about in your book is memory. So in order to create a memory, there's many different stimuli involved in that as well. Sight, touch, hearing, smell. are also part of memory storage components or stimuli for memory storage. There's two stages of storing memory. You have short-term storage and you have long-term storage. So short-term, temporary holding place for little bits of information, limited to 7 or 8 pieces of information. How many numbers in your phone number?
7.
Wonder why? Why do you think? You ever call information? Do, 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 do. No. And the little lady now says way too much. Correct? All right, I'll give you an example. So the little lady says, blah, 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 what's your number, la, 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 and you tell her what the number you want, and then she comes back with the number. Da, 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 da. Then she starts talking again. What happens? You forget, because she disrupted your short-term memory. For me, I have to hang up the phone very quickly so I don't hear the little woman talk again. If she talks again, then I have to end up calling back because I forgot. They do it again. Yeah, they do it again. But then, you know, if I don't have a pencil, I don't write it down, I got to call back. Ever happen to you? That's short-term memory. So very few bits of information. That's really quick. But how am I going to remember that number for a long time? Long-term memory. I either associate it with something or I do what? And this is something many of you don't do in this class.
Study. Eat breakfast.
Write it down! Yes? Get the pencil, write it down. Guess what you did? You made another connection to your file, that phone number, by writing it down.
That's why cell phones are
Cell phones are really bad because now I don't know half of people's phone numbers. What's so-and-so's phone number? I have no idea. It's in my cell phone.
No, it's more like, what's your phone number?
Yeah, that too. So long-term memory is going to put it in a file drawer. We have limitless, scary capacity for long-term memory. We don't even use most of our file drawers in our lifetime. So this diagram on page 456, figure 12.20, tells us some of the pathways to create long-term memory. So remember, I talked to you about some of the other stimuli you should use when you're trying to create a long-term memory. The long-term memory I refer to is studying for your exams. So if you use some of the other stimuli besides just hearing, like what? Pictures, diagrams in the book. What else? Write it down. And remember the smell thing? I did that little trick I told you with the gum in your mouth or the Tic Tac in your mouth or some sort of smell. Add that to the mix too. And that's going to help you create long term. It's going to help you store things in short term, and then repetition is going to help you create long term memory. So that's all of the things that you have to do to create those long term memories for yourself when you're studying. When the data is lost permanently, your file gets thrown away, the data is never allowed to be retrieved. So if groups of nuclei die off during an infarction, for example, groups of your files may be lost forever. The nice thing is, depending on what area is affected, you have plenty more file drawers to recreate new files. And again, it's dependent on what area of the brain is affected. If it's connections to very vital areas that are lost, many times those can't be retrieved. But if small areas die off that still have plenty of room for more storage, you can create more storage. So transmission from short-term memory to long-term memory, some of the different things that are involved in that transition are emotional state. Best time to transition is if you are alert and awake, if you are motivated.
Is that why, like tragic incidents, things that really stay with you?
Yeah.
It's because of the emotion.
Because of the emotion involved in the transmission from short-term to long-term. Motivation. Believe it or not, your motivation level can determine whether or not you're going to do well on that test. If you're highly motivated, you tend to perform all of these actions more often than if you're not highly motivated. Surprise and arousal can also lead to better storage of long-term. Rehearsal, repetition, practice. Association. If you associate whatever it is you're trying to learn with something that already has a big file in your cabinet, it's going to be easier to retrieve that memory. So when you have to go and memorize the 12 cranial nerves, they give you little tricks in the book to help you with that. What are those things called? They're called what? What do we call them? When you make up a little rhyme for something? Mnemonics. Yes? So sometimes that's what it takes to memorize, say, a list of words that normally wouldn't make any sense to you. Make up a little mnemonic. They give you a couple in the book. Best ones are the ones that you make up yourself because you own them. Yes, they can be dirty. Just don't write them down anywhere. But those are the best ways to remember things sometimes when you associate them with a mnemonic. So, categories of memory, we can have declarative or fact memory, very explicit information, related to conscious thought, related to language, that's what you're learning in your class, stored in long-term memory with context in which learned. Or we can have less conscious and unconscious memory through experience and repetition, hard to unlearn.
So some people listen to, like, for learning, they'll put it, say, like their CD player, they'll tape record themselves, say the lecture, they'll play that while they're sleeping. Is that actually, will you retain that information?
Some people record their messages and listen to them while they're sleeping? Yes. No. Just before they fall asleep? Yes. So one of the things I used to do to study was that, because you tell me, I won't forget. So one of the things I used to do to study for my classes, especially when I had the little ones running around and I actually had to feed them, because they do want to be fed, I would tape everything I needed to know from my notes and listen to that recording over and over again. A, giving me the stimulus that helps me learn best, auditory. B, giving me the repetition I need to help store those long-term memories. And then I would listen to it just before I fell asleep. Actually, sometimes it would put me to sleep, and I'd wake up with the buds in my ears. But remember, your best learning happens when? When you're in those alpha waves. So when you're just starting to lay down and relax, listen to it then. Are you going to retain it when you're asleep? No. Because then you fall into that unconscious realm. But right before is when you're going to retain some of that stuff. So, brain structures involved with memory. The hippocampus surrounding the temporal lobes are going to help me with storing memories. What's ACH? Acetylcholine from the basal forebrain is necessary for memory formation and retrieval. And this is sort of the pathway that information takes for storage in the brain. We see this on page 457 in your textbook, figure 12.21. So, some of the brain structures involved: basal nuclei, that sensory stuff, that awareness stuff associated with the thalamus and the premotor cortex. Your motor memory, remember your cerebellum is also involved in helping with memory and retention. And then your emotional memory, that amygdala, that's also important in storing memories and forming long-term memories. So, neuronal RNA is altered during learning. That's the RNA in your neurons. We make more messenger RNA that moves through the axons and the dendrites. What was messenger RNA for? It creates copies of what? DNA, right? For what? Carry on new what? Who? No? Synthesis of what? Proteins! Yay! So I make proteins during learning. I actually change structure when I learn something in the brain. And it has to do with the extensions or the processes of neurons, those dendrites and those axons. Dendritic spines are actually going to change shape during the learning process because of this. Any extracellular proteins deposited in the synapses are going to be involved in long-term memory storage. You actually change structure when you learn something and create long-term memory. So your brain structure, the roads, let's say, leading to information in your brain have changed a great deal from the time you were born to now you are an adult. Some of them weren't even there, and you created them. So number and size of presynaptic terminals may increase, so I can get more information and fire off more neurons during long-term memory storage. And presynaptic neurons release more neurotransmitter during long-term memory storage. So these are all of the things that actually change in your brain when you create a memory. Long-term,
So the dendrites actually grow and
create more branches. So long-term potential, LTP, is an increase in synaptic strength and is crucial for memory building. Neurotransmitters are also extremely important in firing off neurons, creating those pathways to information during memory storage. Calcium influx at the end of those axons that we discussed when we discussed action potential are also going to be activated by enzymes that are going to increase neuron transmission during memory storage. Who protects the brain? Now we're on to page 458-ish, 459-ish. The skull. One of the strongest body cavities you have. Your football helmet. Yes? That's going to protect the cranial region. The other thing that protects the brain is something called the meninges. And the meninges are a series of membranes that produce fluid and provide protection and cushion. The fluid that helps protect the brain is cerebrospinal fluid. And then the last line of protection for your brain are the cells that are going to only let very certain things into that cerebrospinal fluid, your ependymal cells, which are part of your blood-brain barrier. So, what are the meninges? Membranes that cover and protect the central nervous system, your brain and your spinal cord. They're going to help hold blood vessels in place and protect blood vessels from damage.
Does it run the whole length of your spinal cord?
Actually past your spinal cord. We're going to talk about where the spinal cord ends too as well. So your central nervous system contains cerebrospinal fluid, and it's going to flow in between those meninges as well, and also forms partitions in the skull, separations in some of those very deep folds that we talked about earlier in the fissures of the brain. Meninges are going to come down into those to provide added extra protection so that your brain doesn't move around too much in the skull. 3 layers, the dura mater, that's the tough mother on the outside. In between of the 3 layers, we have something called the arachnoid mater, which is kind of like spider webby almost. Now, do you know why we call it arachnoid? What's arachnoid? Spider. And then pia mater means gentle mother. And that's going to lay right directly on the nervous tissue itself. When there's any infection or disease associated with the meninges and they become inflamed, we call it meningitis. Why is that a problem? Yeah, more pressure. So now we're defeating the purpose of having all that wonderful fluid and cushion because we're creating a great deal of pressure on the brain and spinal cord, and that can be life-threatening. So inflammation of the meninges or meningitis can be a huge problem. So we see some of the layers in this diagram on page 459 in your textbook, figure 12.22. We see skin over, what's that white thing there? Periosteum. There's not a lot of muscle up here in your noggin. As a matter of fact, if I take my hand and I move it back and forth, my forehead moves. How come? It's creepy, isn't it? My sister can do that and her whole head moves. It's kind of creepy. But there's muscle here and there's muscle here, and this big, it's called the aponeurosis, periosteum layer there. Underneath that, we have bone, skull, flat bone, bone sandwich. And then under that, we have the dura mater, which has 2 layers. And what did dura mater mean? Tough mother, the tough layer. When you dissect your sheep brain, pay close attention to that because it's going to be covered in dura mater that you'll have to remove in order to go into the brain. It consists of 2 parts, the periosteal and the meningeal layer. Periosteal near the bone and the meningeal near the other meninges. The arachnoid mater, this is this little spider webby thing that's running through there. This is where we're going to find blood vessels and all that good stuff. There's some space in there where we find spinal fluid. And then the pia mater actually sits right directly on the brain matter itself. Is it labeled in this diagram?
Yeah, that's right there.
There it is. So it's this. That sits right on the tissue.
Is the periosteum connected to the bone? Is it like
No. Well, the periosteum of the bone is, but the periosteal layer of the dura mater isn't.
Right.
Yep.
So between the skin and the bone, that periosteum.
The periosteal layer
is
of the dura.
connected to the skull itself.
No.
She's talking about the actual periosteum, not the
Right below
periosteum
the
layer.
skin.
This periosteum is not connected to the bone. It's sort of above the bone. There is a periosteum on the bone too. But this periosteal layer of the dura mater is not connected to the bone. It's just up against it. Make sense? So Duromata, very strong meninx, plural or of meninges, or singular of meninges. 2 layers, fibrous connective tissue, separates or separated to form the dural venous sinus. Limits excessive movement by flowing into those fissures, and these are some of the areas where you see the Duromata flow down into some of the major fissures, like the longitudinal, for example, along the vermis of the cerebellum, and then in a horizontal fold over the cerebellum in that transverse fissure that separates the cerebrum from the cerebellum. So these are just thick areas of the Duromata. This is an actual skull, and we can see them flow into these spaces. So this actually folds into that crease. We see a very thick area, also associated with a lot of blood vessels that are held in by these Duromata or the meninges to help feed the brain as well. Pay close attention to those when you dissect your sheep brain. Then the middle layer, the arachnoid. This is where we're going to see a space for cerebrospinal fluid in the subarachnoid space underneath the arachnoid layer. We find a lot of large blood vessels there. We also see groups of protruding tissue called the arachnoid villi. And this is where I'm going to kind of suck back into the circulatory system old cerebrospinal fluid. So I'm constantly making brand new cerebrospinal fluid with those ependymal cells, and I get rid of all the old stuff in the arachnoid villi of this region. We see those little arachnoid villi again here, very close to major blood vessels. So we suck back into the circulatory system the old spinal fluid. So you're always making fresh and brand new and getting rid of old. And then the pia mater, very delicate, vascularized connective tissue that clings very tightly to the brain. Cerebrospinal fluid is made up of. We'll continue on Tuesday of next week. Listen, just because you don't have a quiz on Tuesday, you need to study this stuff. Yes?